Okay, today we are going to be looking at empirical formula. This kind of builds on what we did last day where we were looking at the percent composition of different elements in a compound. Here I'm going to show you an example. In this example here, we were looking at some sort of nitrogen-oxygen compound. We knew like the total mass, we knew how much nitrogen contributed to the total mass, and we could figure out how much oxygen contributed to the total mass of 4.6. But in the end, we didn't know what the formula for the substance was. We were just able to say, okay, the percent composition of this compound, whatever it is this, okay? So what you're doing today, essentially, is you're going to look at like the percentage here. So if we just write on here. So in this case here, we have 30%, so I'm just rounding it up, of nitrogen that was found, and for oxygen it was rounding up here 70%. Okay, so of the 4.6 gram total sample here at the top, you found that 30% of that mass is nitrogen and 70% of that mass is oxygen. Okay, so what we're doing today is we're going to try to build a formula called an empirical formula, where you are now going to use that mass data and propose a formula that would represent a mass ratio of 30 to 70 of nitrogen to oxygen, okay? But one thing is that you can't just take the mass of nitrogen, like one atom of nitrogen, and compare it to the mass of one atom of oxygen. You need to compare using a different set of units. So again, nitrogen, oxygen, they have different masses, they are different sizes and so forth. So what you want to do is you want to change them to moles, okay? Because remember, moles is like counting in dozens. It's a counter. So if we can convert everything to the same type of units of moles, you can compare them, okay? You can't compare them right now if it's masses. So once you get it to moles, then you're going to use this ratio of it's 30 to 70, okay, in order to build our formula. So that's what we're doing today, but we're going to be just leapfrogging from the information that we learned from last day. Okay, so let's just kind of go over just the technical definition of an empirical formula. This is what we're doing today, and we're going to move on into molecular formula next day. So you're trying to come up with a chemical formula that represents the mass information, percent composition information that you are given. So just keep in mind that the empirical formula is going to be the simplest formula that represents the compound, but not necessarily the chemical formula that you need, that we've been using and naming and so forth throughout the last few units, okay? So it's derived from experimental data like mass data, percent composition, and so the steps that we need to follow are, so we're going to get our percent composition by mass, which is what we did last day. So taking that percent, we're going to convert it to the mass. We're going to relate it to mass and change it to moles, because we cannot compare an element to another element if it's in mass values, okay? Because they have different atomic radii. You can't, it's like comparing apples to oranges. You need to get it to a counter unit in moles. So for example, I can't compare an apple to an orange, but if I change it to like I have a dozen apples and a dozen oranges, I can compare them and say, oh, I have the same number. Okay, where if I have 2 dozen of that and 3 dozen of that, I can compare those values, where you can't just compare an atom to another atom, like mass-wise, okay? Because just think of it, it's not the same playing ground. But if you can get everything to moles, then you're on the same playing ground and you can compare them. Okay, so once you do that, you're going to find the mole ratio. So this will make sense when we start doing some examples. And then we can present some subscripts. So if we feel like there's 2 nitrogens to 2 oxygens, we'll say N2O2, okay? And again, I'm just pointing out empirical formula isn't the actual chemical formula. Not like sometimes it is, but a lot of the times it is not the chemical formula for the actual substance, okay? It's just kind of more of a backbone formula to represent the ratios of, this atom to that atom and so forth. So, like here, I wanted to show you an example here where we have ethine. So it's kind of like, so it has a formula like this is the actual chemical formula, C2H2, and benzene has a formula C6H6, okay? And if you actually reduce both of those, you can get to CH, which is like, a subscript of one, subscript of one. So when you reduce both of these, they both go to the same empirical formula here. So that's why, so just keep in mind that, I might say find the empirical formula CH of ethine, but it's not actually the chemical formula. The chemical formula is CH, C2H2, and that's what we'll call the molecular formula here, okay? For now, we're just going to build our empirical formulas today. But just so we can kind of ease into where we're trying to get to is we are trying to eventually build the molecular formula. And so this will be, the actual chemical formula that we've been using to represent the molecule, okay? So it tells you the actual number of atoms that you need in a substance, okay? So here, the empirical formula for ethine was CH and benzene it was CH, but the actual molecular formula, it should be C2H2 and C6H6, okay? All right, so we'll get right into a question here. And yeah, but we'll just go as far as empirical formula today. Okay, so here's another example just before we start. So we have methanol. So it has a regular molecular chemical formula of CH2O, ethanoic acid. Okay, if you're taking a look, this is the usual chemical formula. But if you look at both of them, you could reduce it down to like a skeleton empirical formula of, see how they both have, like you can divide this one by 2, this one by 2, this one by 2, so you can get a formula of CH2O, like that, and then it looks just like the methanol formula, right? So that's why you got to make sure you know what you're finding and so forth today. But so keep in mind that some empirical formulas do actually represent the chemical formula of a substance as well. Some don't. Like here, this one you had to multiply by 2 to get to the ethanoic acid chemical formula. Okay, and then if we were looking at the data that were being presented, so if we ran both of these through a machine, the machine would tell us, oh, well, both of these substances have 40% carbon, about 7% hydrogen, and 54% oxygen. Okay, so it presents us with the same data. So we won't be able to definitively find which substance it is. We could just find the empirical formula with this data. We need some more information, and that's what we'll do next day. Okay? All right, so let's move on to the first example here then. Okay, so we have to find the empirical formula of a compound, and we know the percent composition is 60% magnesium and 40% oxygen. So we know it's some sort of magnesium to oxygen compound. So if you're just looking at the general form here, we know that it's so we know that it's some sort of magnesium, some number to oxygen, some number compound. And I know you guys can actually build this formula already just with how we've been doing nomenclature and how ions come together and so forth. But let's just pretend we don't know that. But I'm giving you the data that the magnesium is 60% to oxygen 40%. So how do we come up with the empirical formula? Okay, so we're going to just write down that information that's given to us here. So we know that the percent composition of magnesium is 60%. And we know the percent composition of oxygen is 40%. Okay, so it's like carrying on from those last questions we did last day. All right, so we know the percentages of whatever mass this substance is. So we don't know the total mass. We don't have any information about the actual mass. So you can arbitrarily assume, let's just say we have 100 grams of sample. All right, so let's just say we have 100 grams of sample. So if we had 100 grams And we're finding that 60% of the sample is made up of magnesium. So what mass would that be? So you just take the percentage and convert it to mass. Okay, so let's say so if you take 60% of 100, you would have 60 grams of the sample of magnesium, right? And then if you take 40% of the 100 grams, you would get 40 grams. Okay, so again, we don't know how much sample we have here, so we're just kind of deciding, okay, well, let's just say we have 100. Okay, so in this case here, if it's 60%, then 60 grams would be of the 100 would be magnesium, and 40%, so 40 grams would be oxygen. Okay. Okay, so so now that we kind of have a breakdown of what the masses are, we're going to now try to compare them and try to figure out, okay, what the formula will be. So again, like I said, you cannot compare masses, okay? You can't compare the mass of magnesium to oxygen because they have different atomic radii and they will be, so it's different sizes, there's different masses involved, and so it's not okay to compare them with mass, okay? So what you're going to do instead is you're going to compare, put them in moles so you can compare them, okay? So compare them. So here, just make a little note. Okay, so yeah, compare them in moles, not in mass units. So we're just going to kind of list them off here. So we know the mass at first. Okay, so mass of magnesium and the mass of oxygen. So we know it's 60 grams and 40 grams here. Okay, and then we need to get them to moles. So, so I'll write moles down here. How do we get from mass to moles? Okay, so that's a little bit of review from before. So on our formula sheet, so remember we want to go from mass to moles island, so you need to use the molar mass, and in this case here we need to divide by the molar mass. So let's go and quickly calculate the molar mass. So we know we have to divide by the molar mass here. Okay, so the molar mass of magnesium, just look on your periodic table. So for just the one, it's 24.31 grams per mole. And then here, oxygen is 16 grams per mole. All right, so if you divide those out, you'll find the amount in moles, okay? So again, I know I say moles a lot, but this is the amount, okay? But it's in moles. But I'll probably keep writing moles, so just want to point that out if you're just confused as to why I keep changing it. So, all right, so if we divide that out, we end up with a 2.4681. So I'm just carrying a few extra digits here. Okay, here's the amount of moles for that one. And 2.5 moles. Okay, so again, we can't compare masses, so we had to convert it by dividing by the molar mass. Now we're in mounts, so think of this as now, you know how many dozens that you have. So you have 2.4 dozens, and you have like 2.46 dozens, and you have 2.5 dozens of oxygen. So hopefully you're seeing here that there are slightly more oxygens to magnesium here, okay? But it's pretty close. So from here, we're going to do a mole ratio. So the mole ratio step is I'm just literally taking the lowest one here and comparing it to all the other ones that I have, okay? So in this case, we only have one other one, so I'm just going to take, so for example, oxygen is 2.5. I'm going to compare it to the moles of magnesium, okay? And magnesium, I'm just going to compare it to itself. So you always divide by the one that has the lowest number of moles here. So here, the reason why we do this is we're trying to find the ratio. So for every 1 magnesium that you have, you will have 1.0129 mole, or like amount of oxygen, okay? So basically it's a 1-to-1 ratio here. Okay, so this is the mole ratio. So again, you started with the mass. You needed to get to amount in moles, so you divide by the molar mass. Once you got your amount, I wanted to make a comparison with all the amounts, okay? So I wanted to see, is it a 1 to 5 to 7 ratio? Okay, so what you're going to do is you take the one that has the lowest amount in moles, and you're going to divide that through everybody. So again, some of the ones that you're going to have in the next examples will have more elements, and you're going to divide them, and then you're going to see the ratio. So yeah, you need a 1-to-1 ratio here. So in that case there, so now we're going to go and build our formula here. Okay, so we had a 1-to-1 ratio, so just check it in. There it is. We don't write the 1. So in the end, this here is our empirical formula. Okay, so I'm going to call it EF, so I don't have to keep writing it out. Okay, all right, so that's your empirical formula for magnesium to oxygen here. All right, so you were given some initial percent composition data, and then from there we took, adjusted it so it was in mass units, converted it to amount by using molar mass, and then from there we did a ratio, like how do they compare to each other, and we found that it's generally a 1-to-1 ratio, and so we can say that for every 1 magnesium there's 1 oxygen, okay, and then you present the formula here. All right, so then, write your therefore statement, therefore the empirical formula is magnesium and oxygen, like that. Okay, so just keep in mind that may not necessarily be the chemical formula, but it's kind of like a backbone skeleton formula to represent magnesium and oxygen when they combine. Okay, but we know that this is the actual chemical formula because we've practiced these a lot. All right, so let's move on to the next one. Okay, so for the next one here, write the empirical formula for a compound with the following percentage compositions. So we are given, so we know the percent composition of aluminum is 20.2%. Okay, and percent composition of chlorine is 79.8%. Okay, all right, so from there we're just gonna again assume we have a 100-gram sample of this aluminum chlorine compound, and so from there we're just going to convert these percentages to mass. So if we had 20.2% of a 100-gram sample, we would have 20.2 grams. Okay, and if we have 79.8% of chlorine of the sample, we would have 79.8 grams, like that. Okay, so we're making the assumption that we have like a 100-gram sample. Okay, so from there we are looking at finding the empirical formula. Okay. So I don't know if I did that in the last unit. I think I forgot, but I meant to write that. We had to find that. Okay, so here I'll just add it in. Okay, so you have to find the empirical formula. All right, so here's our plan. So we're going to go through and we're going to change everything to moles, and then so we're going to go from mass to moles, which is amount, to a mole ratio. Okay, that's the plan. All right, so let's start with just kind of making a little table here. So for the mass, we know the aluminum contributes 20.2 grams for a 100-gram sample, and chlorine is a 79.8 gram mass here. Okay, and then we need to get to moles. So in order to get to moles, our amount in moles, so it's going to say both, we need to divide by the molar mass. Okay, so the molar mass, you find it by looking at the periodic table, and we know the mass of aluminum is 26.98 grams per mole, and the chlorine is 35.45 grams per mole. Okay, so let's divide those out and write the amount of moles that we will get. Okay, so for aluminum, so again, we need to convert to moles so we can compare them. I always carry a few extra digits here, so like 5 digits after the decimal. And this one here, oops, is 2.25. Okay, so then from there, so now that we have amount, we want to go to the mole ratio. Okay, so I'm going to take the smaller value of the amounts here, so aluminum, and I'm going to divide everybody by aluminum's amount. Okay, because again, the reason why we do that is then we will know, okay, so if I divide that by itself, I'll have 1. So if I have 1 aluminum, how many coppers do I have? So we're going to divide the amount here. Okay, and then we end up with, a decimal like that, but it's pretty much 3, okay? So the mole ratio here ends up being for, aluminum to copper, ends up being 1 to 3. Okay, so the empirical formula, therefore, then, is 1 aluminum to 3 chlorines like that. But we don't write the 1, right? So we just write AlCl3 like that. Okay, so therefore, that's the empirical formula. So don't abbreviate it like empirical formula in the final statement. Just actually write it out. So the empirical formula is AlCl3. Okay, all right, so there's just another one where it's nice and simple. We just have just a couple elements like that. Okay, so we're going to look at one that's a little bit more complex where the mole ratio doesn't come out as nice, so we have to adjust, okay, the ratio before we can present an empirical formula. Okay, so let's move on to the next one here. Okay, so before we go into the next example, I just wanted to kind of point out sometimes when we get to this step here, so, we want mass, molar mass, amount, and then we divide by the smallest amount so we can get our ratio 1 to something else. So sometimes this mole ratio part here, you can end up with some little, some decimal answers that aren't quite a whole number, okay? So like it might be somewhere like 2.5. So you're like, is that 2 or is that a ratio of 3 and so forth, right? So I know normally we'd round up, but it's just a big bump up. So I want to give you an example here. So the step right here, the mole ratio step, so right here, so you might find that you have a scenario like this where you end up with carbon to hydrogen, so here's the mole ratio, okay, of 1 to 1.33. So we want nice values like this where it's 3.00, okay, so it's right on close to being right on the dot there. But when it's like a little bit off, even by 0.3, it's a little too far off, and it's so we need to get it to a value that that will be more like a whole number, okay? Because right now it's like for every 1 carbon, you need 1.3, so you need 1 hydrogen plus a third of a hydrogen, and we don't have thirds of hydrogen, right? We need actual whole number amounts of hydrogen to attach to our compound. So what it is in this case here is that we just have to multiply up by factors to get it to a whole number. Okay, so that's what we'll do here first. So I just kind of go up one by one. So I'm going to start with the first one. I'm just going to multiply by 2, okay? So I'm going to multiply both of these factors here by 2. So the 1 by 2 and the 1.33 by 2. So if I do that, I'm going to get a 2 to 2.666 ratio. Okay, so here it's all right. Like again, it's a little better, but it's not quite close to being a nice whole number. So right now we have the ratio is 2 carbons to 2 hydrogens and 0.6 of a hydrogen. So same thing, we can't have that. So this bump up of multiplying by a factor of 2 didn't work. So let's try 3 instead. Okay, so we're going back to the original here, and we're going to multiply those ones by 3. So if we do that, so carbon times 3 is 3. Okay, and if we take this 1.33 and multiply by 3, then we get to, and that's quite close. Okay, so if you're off by like a 0.5, if it's like 0.5, 0.6, 0.3, 0.4, those are too far off. But 9999, okay, that's good. That's like 3 to 4. Okay, so that is a much better mole ratio that we need to work with, and we can say, oh yeah, then therefore there's, so again, like we're looking at this here. So right now we were trying to figure out what subscripts to write here. So, 1 to 1.3 hydrogens doesn't make sense. So here, when we get to here, a 3 carbon to 4 hydrogen works nicely, okay? Because 2.6, like 0.6 of a hydrogen, no, we can't have that. So a 3 to 4 ratio, that's what we need here. All right, so that's what we need to do in these next following questions. So sometimes it comes out really nice, like these examples where it's like 1 to 3. Oh, perfect, that's easy, okay? So 1 to 3 ratio. But if you end up getting a ratio like this where it's not close to a whole number, then you need to multiply up the ratios until it comes out to a nice whole number, okay? All right, so keep that in mind as we go through. All right, so we need to find the empirical formula for this substance that has iron and oxygen in it. Okay, so here's one we can't guess the formula because we don't know what iron it is. Is it the 2+ iron? Is it the 3+? Okay, because if you look at the periodic table, you'll find that they have different valences, right? So they can sometimes be 2+, 3+, and then we need to figure out experimentally which one it is. Okay, so that's what we're doing here. We're going through, we ran it through the machine. The machine told us that there's a 69.9% iron amount and 30.1% by mass of oxygen in this compound, okay? So again, we want to work in mass here. So we're just going to convert these just to grams like that. Again, making the assumption that there is a 100 gram sample that we're using. So if we have a 100 gram sample, that's the mass that we'll have. All right, so again, we need to find the empirical formula of, and here we can even write it like it's some sort of compound that looks like this, okay? So we need to figure out the x and the y. All right, so our plan here, the usual, okay, go from, we went from percent composition, right? Then we went to mass. Then we went to amount in moles, okay? And then we need to go to mole ratio. Okay, and then we can get to the empirical formula, okay? All right, so let's set up our table here. So we'll write down the mass amounts. So we have iron and we have oxygen. Okay, and we need to get to the amount in moles. So we're going to divide by molar mass. Okay, so go to your periodic table, figure out the molar mass of iron. And the oxygen is 16. All right, divide those out and tell me the amount in moles. And always carry several digits. I always carry like at least 5 or 6 of them. Okay, so there's the amount of moles there. Okay, so we now know the moles of oxygen and iron, so now we can use it to compare. And again, we just want to get 1 to 1, and then the rest, it's like, is it a 1 to 2 ratio, 1 to 3 ratio, and so forth. So the one that we're going to get to 1 is the one that has the lowest, the lower amount of moles. Okay, so here iron is lower. So I'm going to divide iron by itself, okay, and you're going to divide oxygen by the iron amount here. So because we're trying to find the ratio of, well, okay, so since iron's the little one, how many oxygens to iron do we need? Okay, so once we do that, we'll get to our mole ratio here. Okay, so that one's 1, and then there's no units because you divided them both out. So it's just a ratio here comparing, how many dozens, how many moles they have. Okay, and so this one ends up being 1.5311. Okay, all right, so here is an example of what we were looking at above, where it's not coming out to a nice whole number for this one here. Okay, so right now I need 1 iron to 1 oxygen, but also half of an oxygen, and we can't have half of an oxygen. Okay, so this is the part where we need to kind of bump up. Okay, and multiply these up so we can see if we can get to a whole number here. Okay, so hopefully you're seeing, oh yeah, this is going to work on that first check. So what I do when we get to this part here is I will make sure you did all your work correct. Okay, and then from there, then start multiplying 2, then 3, then 4. If you're hitting like, I don't know, 7, 8, 9, 10, something probably went wrong, because usually it's just like maybe 4 multiplications sometimes. Yeah, anyway, so if you're like hitting up close to 10, it's likely that you made a calculation error somewhere. So you just go back and double check your work, okay? All right, so in this case here, I just had to multiply by 2, and now I have a nice whole number of 3 to a whole number of 2. So when I go into the mole ratio here, so again, I'm trying to figure out my iron to oxygen ratio. So we're finding that it's a 2 to 3. So when you go to, fill in your empirical formula here, you just go, oh, well, there's 2 irons to 3 oxygens, like that. Okay, and again, that is your empirical formula. So make your therefore statement. Okay, so hopefully, after these examples, you're feeling pretty comfortable. Try the next one anyway, and then go practice the worksheets and try the checkpoint. Empirical formula is. But again, when you write your therefore statement, write your answer, but also write your key word here. All right, let's try the next one. Okay, so far we've seen like 2 elements. So here's one, there's 1, 2, 3 elements that we have to deal with. Okay. All right, so we have, so again, some people ask every year, do I have to write all this information with the given and the required? No, you don't have to do graphs if you don't want to. I think it's a good problem-solving technique to pick up, though, just because you're doing, much simpler questions right now in high school compared to what you'll do later on. So just being able to have some sort of organizational way of writing down what you have and then what information you need to find does help, I think, going forward. So, but again, I'm not marking this part here. I'm not expecting it. I usually just want to see some work and then your answer and so forth. Okay. All right. So yeah. So if you wanted to go from like this information about percent composition and just go right away, oh, okay, I'm just gonna write the mass. Okay, like that. And if you didn't state that you had a 100-gram sample, it's okay. But just, I guess, just go with whatever your instructor wants you to do. Okay, so I've converted them all to mass amounts. So again, I need to find the empirical formula of, it's going to be a carbon to hydrogen to oxygen substance, okay? So we need to figure out those subscripts. And again, we're just finding the general kind of skeleton, usually formula for these substances. We'll look at finding the actual chemical formulas next day. But for now, this is what we're doing. Okay, so our plan again, go from mass to moles to your mole ratio. Okay, so that you can get to your empirical formula. All right, set up our table. Okay, so we have mass, carbon, hydrogen, oxygen. Okay, all right, so we have 52 grams. Okay, there's the mass of those. All right, divide by molar mass. Okay, going to the periodic table right now. So carbon is 12.01. Hydrogen is 1.01. And oxygen is 16. So hopefully you're grabbing these so often that you have them memorized, okay? So then divide these out to get the amount in moles. And then carry some extra digits, please. Don't round it up to 4. All right, 6.15. I think this was rounded up to 6 here. Okay, and this is 6.0891, I guess. All right, and 41.25. Okay, so there we go. So there are the amounts in moles. Oops, I forgot to write the units. So now I want you to make a comparison. Okay, so which one has the lowest amount here? Okay, so oxygen. Oxygen's the lowest amount. So we're going to make oxygen 1, and then if there's 1 oxygen, how many of the other ones will there be? Okay, so we do that by dividing out the lowest one. Okay, so I'm dividing it all here. Oops. Okay, so this one's 1, and then this one will be 2.333635. Okay, so hopefully you're already seeing that you know you're going to have to bump these up because that's not a good whole number. It's not close to a good whole number. Okay, all right. So yeah, like that. Right now it's like if I have 1 oxygen, I have 1 and then like 0.7 of a carbon. This one I have 2 hydrogens and 0.3 of a hydrogen. So we can't have those fractions of a atom. So let's bump them up so we can make it work. So again, where do you start? Just start at 2. Multiply them all by 2 and see what you get. Okay, so hopefully you're seeing already that's not working. Oops. Okay, so those are still not good whole numbers to work with. So start again. Let's try times 3 instead. So again, go back to the original mole ratio here and multiply those by 3. Okay, so don't multiply the line above that you just calculated. Go back to the original, so 1.67726 multiplied by 3 will make 5.03. So hopefully you're like, okay, that's a nice one. Let's hope the next one works. So we have here times 3, and then this one here is 700,905. Okay, so much better. So here we're looking at a nice whole number that's close to, yeah, so like you have 5 carbons to 7 hydrogens to 3. So here, 3 oxygens. Okay, so that's much better of a mole ratio to compare it with. So here we go. So we have a mole ratio of, let's see here, go to blue. Okay, so we have a carbon to hydrogen to oxygen that we're looking at. So we're looking at 5 to 7 to 3 ratio. So our empirical formula will be, so again, if you like writing the general form here, so you know what to plug in. So it'll be C5H7O3, okay? Okay, and don't forget the keyword. Again, because later on, like, you might be finding multiple things, and I need to know that you understand what it is that you're finding, the terminology for what it is that you're finding. Okay, all right, so I think that's it. Hopefully that was enough examples of, when you don't have to multiply up the mole ratio and when you do have to multiply up the ratio. Again, just looking for that whole number because we're trying to get it down to 1 and compare the other ones. So if they're not looking like nice numbers, multiply them up. And again, if you're hitting like multiply by 10, something went wrong, okay, if you had to bump it up that many times. So just go back and double check your work. But yeah, anyway, so practice. Again, I recommend practice some of the worksheet questions or the textbook questions and then try the checkpoint, okay? So it's about getting ready for next year. And, I'm trying to just go easy with the checkpoints and not make them massive assignments. You still need to kind of do this on your own where you're going in deep and learning how to do something well so that you're ready, okay? All right, so thanks for watching.